Okay, now let's look at again for unpropped and propped. For example, the first thing is due to the initial pre-stress, bottom will be in compression, top will be in tension, right. Then the self-weight stress because of the cast in place concrete, when it is added, again you will have compression at the top and tension at the bottom. Then this is okay, this is due to the girder itself, self-weight of the girder. This is stress due to the cast in place slab. So, this is the CIP. Okay. So, you have this self-weight of the girder will create compression at the top and tension at the bottom. Similarly, the self-weight of the cast in place slab will create compression at the top and tension at the bottom. Now, live loads, when the live loads are going to come into the system, now the entire thing will act as a composite system. So, that is why the entire section will resist the live load. So, that will be coming from the top of the flange to the bottom of the precast web. So, that bottom is going to be in tension, the top is going to be in compression. So, when you add all of them, so this is the resultant stress, right. So, this is your initial pre-stress from the, there will be a concentric component and a pre-stressing moment that effect, then self-weight of the girder itself, then the self-weight of the cast in place slab, then the live load, only the live load will be resisted by the entire composite section. Now, when the section is propped, that means you have lot of additional supports, then what happens? When the pre-stress is transferred, typically that is done in the factory itself where you are producing this precast element, right. So, that will have pre-stressing concentric component, which is your P by A, plus pre-stressing moment effect, which is MP by section modulus, depending upon where you are looking at it. So, when you do that, you will have compression at the bottom and tension at the top, we know that. Now, self-weight of the girder itself again will be resisted and it will create compression at the top and tension at the bottom, same as that case of a unpropped. Now, the difference will come when you pour the slab and then let us say you remove the slab props at a young age, right, because now I have provided lot of props, right. So, now the props will not allow the girder to deflect between them. So, you achieve the composite action in a very quick span of time. So, we are going to have a better composite action at an earlier age. So, the cast in place slab weight, we are assuming that there is not going to be much relative slip if I provide large number of props. So, the entire composite section will take the weight of the slab as a composite section. So, this is the only difference between the propped condition and unpropped condition. And live load, anyway live load when it comes, the age of both the cast in place concrete will be much higher than 28 days. So, the entire composite action will ensure that the live load is getting transferred. So, the only the difference between propped and unpropped is how you are transferring your cast in place slab weight. In a propped section, cast in place slab is being assumed to be transferred through composite action, but in unpropped case, cast in place slab is transferred only as a weight, only by the precast pre-stressed beam. Now, the resultant stresses are going to be here. So, in essence, we can say that the stresses in an propped condition will be lesser than that of your unpropped condition. So, we can look at it. Now, let us look at the analysis of stresses in the precast web at transfer. Let us look at individual case now. Because we are looking at a precast system, we are saying that some losses would have happened in a, let us say, a precast girder. So, the stress I am taking it to be P naught, right. Now, there is an average stress which is going to be compression, and there is a pre-stressing moment MP, which is equal to P naught into E, and depending upon the Y where I am taking at the compression side or tension side, my stresses are going to change its sign. Then you have self-weight moment. Okay, all three of them are acting in the precast web at transfer. Now, stress in the precast web after casting of the flange is this. So, basically when you are looking at casting of the flange or the deck slab, Now again further losses would have happened. So P naught would have gone to PE, right. So the average pre-stress is going to be PE by A. Now pre-stressing moment will become PE into E, right. That is the moment due to pre-stress. Then depending upon the distance of the fiber, my stresses are going to be PE into E into Y by I. Now I am going to have both cast in place moment and self-weight moment of the girder that will be resisted. This is what we are saying is this is for an unprepped, or we should say moment due to the cast in place slab. So into Y. Okay, this is for a composite. Let us say that this is for an, this is a case for an unpropped condition, right, because that is the reason this is being taken like this, right. So that is what we are saying. So stress in the precast web at service, right, it is going to be, so in fact in this case, I am sorry, you going to, after the casting of the flange will be like this, right. So for unpropped condition, this is what we are saying, you have some self-weight plus this everything remains as it is. In addition to that live load, when you put it, that Y becomes Y prime and I becomes I prime. So what is that? That means I prime and Y prime are the section properties of a composite section, right. So here only live load is resisted by composite section, right. But however, in propped construction, you see here both cast in place moment and live load moment are resisted by composite section property. That is why Y prime and I prime come. So that is the reason I prime and Y prime will be slightly higher, but I prime, depending upon where you look at it, I prime will be definitely higher. So the stresses in a propped construction is expected to be lesser because you have higher moment of inertia that you are using for calculating the transfer of your cast in place slab weight. Okay, so these are the nomenclature. A is the area of the precast web, Y and Y prime are the distance of the edge of the CGC of the precast web and CGC of the composite section. Again we have seen E is the eccentricity of the cable and I prime are the moment of inertia of the precast web and composite section, right. Now let us look at one example problem. Let us understand how different stages calculations can be done. So we have midspan of the cross section, which I will show it in a while. We have basically 350 by 1500 mm depth post tension with an initial force of 2500 kilonewton. So you see here this, the web, which is a precast element, post tension element, which is having a width of 350 mm and a depth of 1500 millimeter, and initial pre-stressing force is 2500. After losses, the effective pre-stress force is 2200 kilonewton and the span of the girder is 20 meter. After the web is erected, the top slab of 200 by 1400 mm width is casted. Now after the concrete has hardened, the composite section has to carry a live load of 10 kilonewton per meter. Okay. So this is the cast in place slab and this is your precast element, right. So the live load requirement is 10 kilonewton per meter and the span is given as 20 meter. The density of concrete for self-weight, you can assume it to be 24 kilonewton per meter cube, and we are going to say that the E CIP and E of the girder both are same, is equal to E of CIP concrete. Okay. Now we are going to compute the stresses at various stages. One is an unpropped condition, another one is a propped condition. Now let us look at, first is a calculation of your geometric property. If I take one as precast section properties and area is 350 by 1500, 525,000 millimeter square, moment of inertia BH cube by 12, that works out to be 9.84 into 10 to the power of 10. YB is the maximum distance of the fiber from the CGC, so that is basically 750 and 750. Now cast in place concrete, your area is 280,000 millimeter square and I2 is 9.33 into 10 to the power of 8, and YB2, which is the distance of the element 2 from its CGC, is 100 mm. So, that is this, right, 100 mm. And then composite section properties, now the total area becomes A1 plus A2, which is 805,000 millimeter square. The composite centroid YBC is, as you can see, which is 1045, which is from here. You can see CGC now has shifted up, and now it is at 1045.65 millimeter, and so on. So, these are the properties. Similarly, the top fiber is at a distance of 654.35 from the CGC of the composite section. So, you know how to calculate these properties. Now, let us use it for calculating the stresses. Now, while you do the effective pre-stress, let us say what are the stresses, because we are doing the calculations at certain stage, there is a losses. So, due to the pre-stress, the stress at the top, I should say P effective by A1 in the girder, okay, in the precast girder we are looking at it, P effective times E times YB1 by I1. The one subscript indicates it is for precast girder, and this is your pre-stressing moment MP times the distance of the fiber by I1. So, you can see here the stress at the top of this first element is going to be minus 0.838 megapascal. So, you can see now pre-stressing moment will create tension at the top. A concentric component will create compression. So, that is the reason this is compression, this is tension, right. So, pre-stressing moment, because we are looking at the calculation of the top fiber of the precast girder. Now, how about at the bottom girder? Only the sign will change for this. This will become minus. So, it becomes minus 7.54 megapascal. So, this is the way that we have calculated for the element number 1, which is a precast web due to the transfer of pre-stress. Now, what is the sulphate? Sulphate I have to calculate. Area we have already calculated, multiplied by 24, which is the unit weight, 24 kilonewton per meter cube, divided by 1000 square will give me 12.6 kilonewton per meter. And the sulphate moment, you can see here we get about 630 kilonewton, I would say kilonewton meter. So, because it is about 10 power 6 is, you convert Newton millimeter to kilonewton meter. So, you get 630. And what are the stresses at the top and bottom of the girder? You get moment divided by YB1 by I1, because the section is symmetric, both of them are producing plus or minus 4.8 megapascal of stress. Now, what are the stress due to the sulphate of the cast in situ slab? Again, area of the slab is 28,000 multiplied by 24, which is your gamma of the concrete, right. So, divided by 1000 square, which gives you 6.72 kilonewton per meter. So, that gives me a moment of again 350 kilonewton meter, right. So, if the beam is propped, now again how this, the only difference is going to come is how this sulphate of the cast in slab is being resisted. We have seen that if we provide adequate number of props, there is a better composite action. As the concrete hardens, it develops composite action quickly. The moment when I remove the props, so it is going to transfer the load as a composite section, right. So, if the beam is propped, I get 2.67 megapascal. If the beam is unpropped, if the beam is propped, you can see that I am going to get the moment of the beam times YTC, which is basically right. So, basically it is this. So, basically this is slab, okay, right. So, this is the slab, and I get a stress of 0.99 megapascal. And at the bottom again I am going to get slab, it should be slab here, right, times. So, this will be, if the beam is propped, the M slab will be resisted as a composite section. So, this becomes 1.58. So, you get 3.5 into this divided by this, you get your, you see here, this is your moment of inertia of composite section and this is your distance of the fiber from your CGC, this is your CGC prime. Okay. So, now what are the stresses due to live load? Live load anyway, whether it is propped or unpropped, at that time composite action would be achieved, and that will be taken care as a composite section only. Now, live load is given as 10 kilonewton per meter times L square divided by 8 gives me moment, and that moment if you substitute M into Y by I will give me stresses, which is 1.41 compression at the top and a tension of 2.26 megapascal. Look at now what are the stresses that you have for both unpropped and propped condition. Now, let us look at for the first, when you transfer the pre-stress, that it does not matter whether it is propped or unpropped, the stresses will remain same, minus 0.838 and minus 7.54, both of them will be same. While for precast beam weight, again there will not be any change, 4.8 compression at the top and 4.8 tension at the bottom, and I get 4.8 and 4.8 for the propped condition as well. For cast in place slab, I get 2.67 and 2.67, this is the only difference. In case of an unpropped condition, the weight of the slab will be resisted only by the web, but in case of propped condition, it will be resisted as a composite section. So, I am going to have negative 0.99 and 1.58. So, this is going to be tension and this is going to be compression, right. Live load in both unpropped and propped cases will be resisted as a composite section only. So, I get stresses of 1.41 compression, negative and positive, and this is the value at the interface of your flange and web, that is worked out to be minus 0.98. So, when you add all of them, I get, you see this is the stress, there is no change, either it is propped or unpropped, live load will be resisted by both composite section properties. So, when you look at the stress states, you see here I have minus 1.42, here minus 2.42, that means the compressive stress is slightly getting increased, but that is a good thing because concrete is strong in compression, but we are more worried about what is happening for tension. Tension in case of an unpropped case is plus 2.26, but in a propped case is plus 1.1. So, almost you can see that the stress in tension has reduced by 50%. So, that is the reason we said the stresses, the tension stresses, when you prop it, it will come down in case of a propped construction. Okay. So, now we can also do the analysis using the concept of transformed section. So, let us explain how the concept of transformed section. Now, why do we need to go for transformed section is because my material strength or material elastic modulus for cast in place slab and precast girder can be different. So, you know, we can invoke the concept of transformed section to quickly do the analysis for materials with different elastic modulus. Now, at any level of cross section above y from the neutral axis or CGC, the flexural strain should be same because it has to satisfy strain compatibility, right. So, we can say that the stress in the concrete of the girder by elastic modulus of the girder should be equal to stress in the cast in place concrete divided by elastic modulus of the cast in place concrete, where FCP, FC and FCP are the flexural stresses in the actual and transformed cross section, and EC and ECP are the elastic modulus in actual and transformed cross section. So, we can say the stress is EC by ECP into FCP, right. So, or in other words, the ratio of EC by ECP, right, which are actual and transformed cross section, we can write that as modular ratio, right. M is the modular ratio, which is the ratio of concrete by, if you have difference of elastic modulus between girder and your deck slab, then you can use the concept of modular ratio to calculate the stresses. So, the equivalent section will provide proper resistance if the differential compressive force between the elements are same. So, how do we do that? Let us say, how do I do the integration? The compression is Fc into B into dy. For example, if I take this element as thickness as dy between the transformed section and the actual section. For example, if you look at it, so in the first case it is going to be Bf, actually it should be Bf, right. So, Bf, right. So, this should be Bf, sorry. Bf into dy. So, that should be equal to transform section. This is the red color is basically your transform section, right. So, Bfr into dy should be same. So, then we can write that using that same transform. So, this is the concept. So, in that way we are basically effectively reducing the flange width to make it as a transformed section of higher elastic modulus, right. That is what we are doing. Okay. Now, let us see the same example. Now, if let us try to find the resultant stresses for unpropped condition if the elastic modulus of the precast beam is 35 gigapascal and the cast in place slab is 25 gigapascal. Using these different values of elastic modulus, let us see how do we do the calculation. And this is your standard section we have already done. So, if you take the ratios, modular ratio, if you use a higher value, so it is going to be 35 by 25 is 1.4. So, the area of the precast web already we have done it, area of the cast in place flange which is 280,000 which you have already done it. Composite section, you can calculate the centroid now using the transform section properties 1.4 into 525 because you know this is having higher E, right. So, we are increasing this area, okay. So, that is why we are multiplying by modular ratio. This is 280 times y should be equal to summation of the entire area. So, if you do that, right. So, you take the centroid, then you know you get your y for the composite section is 984.48 millimeter, which are this. So, my CGC is now this. For transformed section it has increased to 984.48, and again the eccentricity or the distance or the cover requirements have not really changed. So, that remains same. Now, the top fiber is at a distance of 715.52 millimeter. Now, what is the moment of inertia? Again, you can use the parallel axis theorem and get your moment of inertia for composite section. Now, that you found your CGC of a transform section, you can use parallel axis theorem. For the web, it is you can see 1400 into 200 cube by 12 plus this area 280,000 times 1600 minus this plus 1.4 into area and so on, the difference. Okay. So, this actually should be the slab, right. So, the slab we are not changing, only we are changing the area of your precast element, right. So, if you do that, you get your value as 2.85 into 10 to the power of 11. Now, let us use for unpropped condition, again the stress due to pre-stressing self height of the precast beam and cast in place slab will remain same because only the live load will be taken as a composite system. So, we use the same concept. Stress due to live load is again it does not change 500 kilonewton meter which we have calculated previously. So, due to cast in place on cast in situ slab, now what would be the load? That is basically 1.25, and what are the slab at the bottom? This is basically the only we are looking at the slab, right, at the slab. This is load and this is the distance of the top fiber of the slab 715. So, that is what we are having. So, we are doing at this location, okay, top of the slab. So, we are doing here. Similarly, at the bottom of the slab you get ys basically. So, sorry, we are looking at this location. So, bottom of the slab. So, this distance is basically 515.5. So, that is the reason you have y here, and moment of inertia for transform section is 2.85. So, you get negative 0.9. On precast beam, again we go through now precast beam. See, precast beam we are increasing the area, so your modular ratio will be higher. So that if you substitute that, your IC is 1.85 rated to the power of 11. And now you see here again we are doing the calculation at the top of your precast element. So Y is 515.5. So you divide by moment of inertia of your composite section. So if you substitute that, you get stress of 1.26. Similarly, how about at the bottom of the beam? So bottom of the beam, my distance is 984.48. Again I apply the modular ratio 1.4, right? So MLL by 2.85, again this, and then when you substitute that, you get a stress of plus 2.41. So if you look at the stresses, the first one due to effective pre-stress minus 7.4 and 0.838, there is no change, and precast beam 4.8, 4.8, there is no change. Cast in situ slab, when you look at it, you get a stress of, again due to the weight, this is weight of cast in situ slab, right? That is again will be resisted only by the precast girder. So that is why there is no change, minus 2.6 and plus 2.6. Now due to live load, if you see, we get 1.25 and 0.9 at the top and bottom of the slab. So these are the values. Then at the top of the slab, you get there is a discontinuity in stresses because of the composite section that what we are doing. So you get a stress of negative 1.26 and a positive stress of plus 2.41. So when you add all of them, you see here you get a stress discontinuity at the interface of the slab and the precast web. Okay, so you see here, so that is what, so when you add all of them, you get a stress discontinuity of about 9.56 that you get, and this is plus 2.2. So this is in tension, this is in compression. So you get maximum compressive stress at the interface of slab and the precast girder.